All right, welcome, grade 10. Let's jump right into it. I am absolutely thrilled to have you here today. Get ready to put on your lab coats, well, metaphorically speaking, of course, because in today's explainer, we are embarking on a massive scientific investigation. We are going to be lab detectives, uncovering the invisible, highly active chemistry of our daily lives. We're talking about acids, bases, and salts. And listen, these aren't just some abstract concepts trapped in a dusty textbook. These are the literal chemicals that flavor your food, clean your clothes, and even operate right inside your own stomach. So let's dive into this fascinating microscopic world. So here is our roadmap for today. We'll cover acids and bases around us, the science of ions, understanding the pH scale, color indicators, and finally, neutralization. Starting right off with Section 1, acids and bases around us, from calamansi to sabon. You know that face you make when you bite into calamansi? You know, when your whole face just puckers up because it's so intensely sour? Or think about taking a shower. Why does a bar of sabon feel so incredibly slippery in your hands? Well, these everyday sensory experiences, they're actually your very first clues as a lab detective. The sour taste of calamansi or vinegar and the slippery, sometimes kind of bitter nature of soap are direct results of their chemical classifications. Simply put, calamansi is an acid and soap is a base. But hey, before we go any further, I need to emphasize the absolute golden rule of science. Actually, scratch that. It's the #1 rule of survival in chemistry. Chemicals must never be tasted in the laboratory. I mean it. While the acids in your kitchen, like vinegar and calamansi, are totally safe to eat, many acids and bases found in a lab, or even in heavy-duty cleaning supplies, are highly corrosive. That means they can cause severe burns and are incredibly dangerous to your skin, eyes, and body. At home, sure, use your taste buds, but in the lab, we use science. Moving on to Section 2, the science of ions, uncovering the microscopic clues. Okay, so to really grasp acids and bases, we first have to understand the fundamental building blocks making them act the way they do. We need to talk about ions. An ion is just an atom or a molecule that carries a real electric charge because it has either gained or lost electrons. When substances dissolve in water, they can actually split apart into these charged ions. And guess what? It's exactly which ions they release that dictates whether they're going to act like an acid or a base. And when we compare these chemical culprits side by side, we see a massive difference. The defining scientific trait of an acid is that it produces hydrogen ions. We write that as H+, when it's dissolved in water. It's those specific H+ ions that give acids that signature sour kick. Now, on the flip side, a base is a substance that produces hydroxide ions, written as OH- in water. Those OH- ions, that's exactly what makes bases feel slippery and taste bitter. So remember, H+ means acid and OH- means base. Let's ground this whole concept in some highly relatable local examples you probably have sitting around right now. Take hydrochloric acid. This is a very strong acid naturally found right in your stomach to help digest food. You know that gross, sour, burning feeling you get when you skip a meal? What we call being liposcutum. Yeah, that is hydrochloric acid doing its thing. Next up, acetic acid, which is the active stuff in suka or vinegar. Over on the basic side, we have sodium hydroxide. This is a very powerful base used to manufacture soaps and clear out nasty drain clogs. And then there's sodium bicarbonate, which is just your everyday baking soda. See, your house is quite literally a chemistry lab. Let's look at Section 3, understanding the pH scale and measuring chemical power. 7. In the world of chemistry, 7 isn't just a lucky number. It's actually the exact dead center of our measurement tool, representing perfect, absolute neutrality. Pure water has a pH of exactly 7, which means it isn't an acid and it isn't a base. It is perfectly balanced. So the full pH scale ranges all the way from 0 up to 14. If a substance has a pH value anywhere from 0 to 6, it's acidic. And here's the trick to remember. The lower the number, the stronger the acid. A pH of 1 is way more corrosive than a pH of 5. Right in the middle at 7, we've got our neutral substances, like pure water. Moving on up, anything from 8 to 14 is basic. And similarly, the higher the number goes, the stronger the base becomes. So a heavy-duty drain cleaner might hit a 14, while a mild baking soda mixture might just sit around an 8 or 9. Section 4 now, color indicators, revealing true chemical identities. Now, what exactly is an indicator? Well, an indicator is a substance that almost magically changes color, depending on whether you drop it into an acidic or basic solution. Some indicators are completely natural, like the juice from a red cabbage. It literally changes color based on the acidity of whatever you mix it with. How cool is that? Others are synthetic, man-made tools specifically designed for pinpoint laboratory precision. Let's break down a quick cheat sheet for the most common indicators you are definitely going to use in the lab. First, litmus paper. If you're holding blue litmus paper and it turns red, boom, you've got an acid. Always remember, red means acid. If you have red litmus paper and it turns blue, you found a base. Blue means base. Next is phenolphthalein. It stays totally colorless in an acid or a neutral solution, but drop it into a base and it suddenly turns this vibrant pink. Finally, the universal indicator. This one's a real game changer because it shows a whole spectrum of colors across the pH scale. It shifts into warm colors like red and orange for strong acids, hits a neutral green exactly at pH 7, and shifts into cool blues and purples for strong bases. Finally, Section 5, neutralization when opposites react. So what happens when you mix an acid and a base together? You don't just get some super chemical. You actually start a battle where both sides completely disarm each other. Step 1. The acid, armed with its H+ ions, meets the base, carrying its OH- ions. Step 2. These opposing ions literally cancel each other out in a rapid chemical reaction. And Step 3, the grand finale, this exact reaction produces water and an entirely new ionic compound that we call a salt. Let's look at the actual chemical equation for this, because it's honestly mind-blowing. HCl, which is hydrochloric acid, a highly corrosive, really dangerous acid, is added to NaOH, sodium hydroxide, which is an incredibly strong, dangerous base. But when they react, they neutralize. The H and the OH combine perfectly to make H2O, safe, neutral water, and the remaining sodium and chlorine atoms lock together to form NaCl. You know what NaCl is, right? It's sodium chloride. That's just everyday table salt. Two intensely dangerous chemicals perfectly neutralize each other to create the salt you sprinkle on your food and the water you drink. No way, right? And this neutralization process is absolutely vital in our daily routines. When the bacteria in your mouth produce acid, what do? You brush your teeth with toothpaste, which is mildly basic, to neutralize that acid and stop cavities in their tracks. When you get that highly acidic lipus guthum stomachache we talked about, you take an antacid like milk of magnesia, which is a base, to neutralize all that excess acid and relieve the pain. Even something as simple as using baking soda to neutralize strong acidic odors in your fridge is a neutralization reaction happening right in your kitchen. While Grade 10, you have officially unlocked the core secrets of acids, bases, and salts. You now know for sure that it all comes down to the delicate balance of hydrogen and hydroxide ions. But I want to leave you with one final thought to ponder today. If our entire world is constantly balancing these powerful chemical forces in the food we eat, in our cleaning products, and literally inside our own bodies, what other invisible chemical reactions are happening right around you, in your home, right at this very moment? Keep your lab detective hats on, stay curious, and I'll see you in the next explainer.